Hello, so back in the YouTube. Yeah, it's kind of weird that my OBS is not cooperating too well, because as soon as I stop streaming, it kind of losing my streaming key. And that's the reason that, again, it took me a couple of minutes to be able to go back online. And I still not sure if I'm online. Still not online. Okay, excellent connection, but live chat is not there. Okay, so it seems that it is up and running, but for some reason I don't get the message to my don't know why I don't get the message that I'm online. So okay, I can see that now the guys you coming into the system again. All right. This is not very convenient. This is not smooth. I kind of don't like this at all. Okay. Anyway, so just prior to break, we'll look at the in-class quiz, and I would like to share the scores of the in-class quiz with you. So this is my Socrates view. So let me make it looking a bit different. So let's see. This time I don't expect the success rate to be too high, because the correct solution is a little bit unusual. I'm kind of guessing that many of you are voting for option the first option, which is not the correct option here, because the correct one is D. Look at this. Look at this. So this is good scoring, 86%. 86%. Only 10% is voting the obvious one. Obvious one is not the correct solution, because the really often used sequence is coming from the gyrus. And as mentioned earlier, you can put the gyro to any orientation in the space. So with that, let's move on and let's look at something that is kind of simple. And kind of simple is that what are the mathematical properties of rotation matrix? This is going to be something that I'm going to repeat over and over again, and this for sure becomes clear to you. So first of all, rotation matrix is orthogonal matrix, meaning that its transpose is equal than its inverse. Physical interpretation of transpose and inverse is that, if the rotation matrix maps description from body reference coordinate system to global coordinate system, then the transpose will do the inverse. So it's mapping description from global coordinate system to body reference coordinate system. So that's essentially what it means. Now this orthogonality means that if you have the transpose of the matrix, and you multiply that, using the transpose of the matrix, and you multiply that by original matrix, the solution will be identity matrix. Identity matrix is a matrix where the diagonal components are equal to 1, rest are 0. Then successive rotations in three-dimensional space are not something that you can change the order, but this is only valid in three-dimensional space, so not too important for us. But these first two things are something that are kind of important for us. Now with that, what follows is that we're gonna move on to a little bit of nasty business. So we're gonna use a little bit of mathematics to differentiate the position with respect to time to get the velocity, and velocity we're going to differentiate one more time to get acceleration. Here's a warning to you. Don't get confused about mathematical details, because those are not important for us. Really, what is important for us is how the final solution look like, and what is that we can learn from the final solution. So, without further ado, let's get started. So let's take our position equation, which is this one here. So this is the one that is used to describe a particle with respect to global coordinate system. And you know that the position and velocity are related in a way that if you differentiate the position, you get the velocity. And if you differentiate your position with respect to time, of course. How that can be made? Well, it can be made mathematically, such the way that you have here partial r, partial t. So you're differentiating this one with respect to time. So this is how it looks. So I'm differentiating these two components, actually three components, kind of, with respect to time. First one is this one here, so it's a partial r, partial t. Second one is the second component, which consists of two components that are rotation matrix and vector u-bar. That too will be differentiated with respect to time. Now, because of these two components, finally my differentiation operation looked like the one that is shown here. Only two of them are important for us, because the last component, which I'm differentiating the vector u-bar with respect to time, will be 0. And that's going to be 0 because remember that the vector u-bar is constant. So it's not changing as a function of time. Why not? Because the body is rigid. And because the body is rigid, so if I have here a potato-shaped body, and I have here body reference coordinate system, vector u-bar that tells the length of the vector, the length, the position of this particle with respect to body reference coordinate system, that vector remains constant no matter what. So it's always a constant vector. So that leaves us two components that we have to deal with. So once we do this operation, we get r dot, which is obvious what it is. So that's translational velocity of body reference coordinate system with respect to global coordinate system. And then we have a little bit more complicated component, which is this rotation matrix dot, meaning that the rotation matrix is differentiated with respect to time. That's something that we need to take a look in detail, because this is a bit more complicated component than this translational component. Now here how it looks in detail. So once we differentiate this rotation matrix with respect to time, so it essentially means that each of these four components have to be differentiated with respect to time. We do know that the theta that describes the amount of rotation that the body is experiencing, it is actually changing as a function of time, because when the body is rotating, this numerical value is changing, as is the case of other four components that are in the rotation matrix. Now, using something that you guys may have heard from previous math courses, or this is I think already in high school, using a chain rule of differentiation, I can carry out this operation such the way that it is, first when I'm doing this operation, I'm going to get the minus sine theta a, and then I'm going to have here partial differentiation of angle with respect to time. This obviously going to be denoted as theta dot, which for us going to be angular velocity. Angular velocity, so what's the velocity? How is the velocity associated to how fast the body rotates? When following the same concept for other remaining three components, I'm going to have here minus cosine theta multiplied by theta dot. Cosine theta multiplied by theta dot minus sine theta multiplied by theta dot. So this is how finally my rotation matrix dot look like? And now you can see that I'm going to take this one here and take it away from the matrix because it's located in every single component in this 2x2 matrix. So once I do that, this is how it finally looked like. Okay, is this important information for us? Well, we're going to use this every now and then. And we're going to denote this one here, this A dot, such the way that is angular velocity multiplied by rotation matrix that is differentiated with respect to angle theta. So this sub index here refers this partial differentiation. Now, when you look at this one here, this one and original rotation matrix are heavily related. And actually, when you look at this one and original rotation matrix, it soon becomes clear that this one here, it is a rotation matrix that is 90 degrees are rotated with respect to original rotation matrix. So it's not that weird component, so it's kind of like, switch a little bit, and that's what it is. Okay, so I got some improvement proposals in okay, so I got the improvement proposal from the chat window which says that I should leave the streaming on. We'll do that next time. I just need to somehow mute it because I would like you guys to be able to communicate with me without end up to being a part of the YouTube video. Okay, anyways, so concluding, the velocity of a particle look like this. So I have translational velocity, and then I have angular velocity, and then I have this component which is a rotation matrix rotated 90 degrees, and my usual friend which is called vector u bar. So that's it. So that's my velocity. Let's take a look at what this means in, well, after a couple of slides. But prior to that, another painful operation, which is we need to move one step ahead from velocity. So once we have this velocity as shown here, we can differentiate that one more time with respect to time. This time I'm not going to go that in such good details and in the previous case, but I'm simply going to differentiate each one of these components. So this one I'm going to differentiate one more time with respect to time. That's going to be r dot dot, which is translational acceleration. Then I have these two components that are not constant components. When I differentiate the one in the middle, I will get this component here. When I differentiate this one here, I will get angular acceleration. Now, something that is not going to be proved here in the lecture, but you can study the detail from the lecture note, is that this guy here, which is the one in the middle, can be written as it is shown here. So it's a minus angular velocity multiplied by original rotation matrix. And once using that information in here, so once substituting that information here, finally the acceleration can be written as it is shown here. Now, you see that acceleration consists of three components. First one is obvious, so that's going to be translational acceleration. Then I have a component that is quadratically related to velocities, angular velocity to be more specific. This component here. This is because the way we introducing the body reference coordinate system. And then we have component that is linearly related to angular acceleration. So these are the three components. And these three components have names, and these names are explained in my next slide. So, well, the first one is clear. So this is translational acceleration component, normal acceleration component due to the rotation, and tangential acceleration component due to the rotation. Now, every now and then you may wonder, like, what about Coriolis acceleration? So where the Coriolis acceleration is in this picture? Well, Coriolis acceleration is not here, because By the definition, Coriolis acceleration takes place when a particle moves in a rotating disk. So let's make a body. This potato-shaped body as a rotating disk. So let me introduce a revolute join to this origin of the body coordinate system. And let me rotate. And once I rotate the system, then I'm looking at the particle here. Now, is this particle able to translate with respect to this body coordinate system? No, it's not able to do that, because vector u bar again is constant. Now it's constant because we are dealing with rigid bodies. So no need to consider about the Coriolis acceleration. There are some good videos that I'm recommending you to take a look that are kind of highlighting the concept of Coriolis acceleration, and those videos are the ones that you can find here. So highly recommended to take a look to make sure that you understand what exactly is the concept of Coriolis acceleration. Well, we do not have a Coriolis acceleration because we are dealing with rigid bodies. Okay, now here comes the little bit like how these vectors are pointed. So I have here particle P again, located here, and its acceleration. First of all, I am describing the translational acceleration of body reference coordinate system here, and then these two components were tangential acceleration and then the normal acceleration. And the tangential acceleration is the one that is pointing this direction. This one is pointing this direction. And this is something that I'm sure that you have experienced when you make a really tight curve in your car. You feel that your body is moving to this direction. This one here requires some angular acceleration to be able to experience that. Now, it sounds like, okay, we got this information we need, and we did that. Now, what's going to follow next is that we're going to leave this description of velocity and acceleration for a side until we started to look a bit more carefully about dynamics. And this time already, it's good you to recognize that our inertial forces will be heavily related to this description of acceleration. And what we have here is that we have an inertia that is linearly related to acceleration and quadratically to velocities. That's something that we need to discuss quite a bit in future. Okay, so let's leave this and let's move on to something that is super important. So now I hope you guys leaving anything else except this streaming. So if you're chatting with your friend, if you're watching Netflix, don't, because you need to follow my next explanation with care. And my next explanation is related to generalized coordinates. So what follows is I will explain this concept of generalized coordinates, and right after that there's a question that I will ask in class quiz. And to be able to answer that in class quiz successfully, it's super important that you're following what I'm about to explain to you. Okay, you ready? I'm ready. Okay. Now, we have this description of particle with respect to global coordinate system. What we need to do next is that we have to identify the variables that are used in this description. And once we kind of are able to identify the variables, then we can express all the other components in terms of these variables. That means external applied forces, inertial forces, and so on and so forth. So the name of the game will change from this on, because we can introduce something that is called generalized coordinates. And these generalized coordinates is a set of coordinates that are used to describe this particular equation. Okay, so those are the ones that are not reminding constant when you're translating the system and when you're rotating the system. Maybe better to say body instead of the system this time. Okay, so we have here, so let me try to take these drawings away. This one too. Okay. This guy back here. Okay. This is a vector that describes the translation of the body reference coordinate system with respect to global coordinate system x and y. Now when the body is translating to say random way like here to here, how is these two components that are inside of this vector, which is rx and ry, are they changing their numerical values? Yes, they are changing their numerical values because they describe how is a translation, where the body reference coordinate system is located at. And these two guys are giving that number numerically. Okay, so those are obviously variables. And because they are variables, they are also our generalized coordinates. Then comes next, guys. So this is a rotation matrix. Remember, the rotation matrix was a trigonometric functions about angle theta. Angle theta describes the body rotation. So it's obvious that one additional variable comes because of this guy, and that's angle theta. Then what is left is this guy, vector u bar. How are the components of vector u bar changing when body is translating and rotating? They are not changing. They remain constant no matter what. Because remember, that was the whole idea in the beginning, and this was a reason that we introduced this body reference coordinate system. So this guy here, the vector u bar, is unable to introduce any additional variables to system. So now when summarizing the situation, so we have variables that are coming from this vector here, which is rx, ry, and then we have here angle theta. This vector here is called generalized coordinates of the body A. These are the ones that we're going to use over and over and over again, and I'm momentarily going to ask in-class quiz related to that. Now the number of generalized coordinates depends on the number of bodies. So if you have, in addition to this body A, you have body B, you need to have 3 additional generalized coordinates, which will be rx, b, ry, b, angle theta b. So that will be a total of 6 coordinates. So if you have here body C, you need 9 coordinates. If there's a body D, you need 12 coordinates. So this is how you increase in the number of variables you need in order to be able to describe the system configuration. These variables are called generalized coordinates. Extremely important concept. Okay, so with that, so let me take my mouse back to this screen. And then let's look at shortly how is a case in a 3-dimensional space. In 3-dimensional space is, and by the way, this is the last matter related to 3-dimensional space. So in 3-dimensional space, we're going to have 3 generalized coordinates associated to translation, and then 3 or 4 associated to rotations. Let's say typically it's 3 because the method we just learned was based on Euler angles, and Euler angles are using 3 rotational coordinates. But many of the really high-end mathematical description of rotations are based on 4 parameters instead of 3, but we are not going to look more details in that. So in 3-dimensional space, one body needs 6 generalized coordinates. So if you have 2 bodies in your system, you need 6 plus 6, which is 12, so on and so forth. So that's how it goes. Okay, ready to my in-class quiz? My in-class quiz is this. A body A. So we are looking at the one body only. How is a vector of generalized coordinates for the one body? So basically the solution is here into this equation. So you need to look at what are the variables in that equation. Options are Rx, Ry, Rx, Ry, theta. U bar X, U bar Y, Rx, Ry, theta, and U bar X, U bar Y, theta. So those are the three options, and hopefully you are still in Socrative. I will put it on momentarily. So it's on. So go ahead and shoot it. One only is correct. One option only is correct. A little bit excited because there is a chance again that I'm gonna score high. Perhaps not 100%, but I think high would be 80, more than 80% would be outstanding in my mind. So let's see. Okay, so still I'm gonna wait, and the last item we're gonna discuss today is constraint equations. Okay, so if the concept of generalized coordinates is important, then the concept of constraint equation is very, very, very important. And this is definitely something that you have to master when you go into midterm exam. And we're gonna look at this in a certain, looking at simple examples. First, we're gonna look a little bit at like concept behind, but then we're ready to move on to examples, and that should tell you how you can describe constraints mathematically, joints mathematically. Okay, so I checked my in-class quiz and I checked my Socrative, and I can see that I have a total of 86 students here in my Socrative, which is a good number, by the way. Out of the 130 something participants, this is a good number. And out of these 86, I have 75 answers in my system. So you made a mistake. You can go. I think you can correct it. Yeah, actually, I'm not sure about that. Yeah, try to change it. Try to change it. I think maybe it's possible to change it. I'm not sure how. I think the settings in Socrative such that that I'm on that the only one shot is allowed. Sorry about that. Sorry about that. Okay, I'm gonna get back to that in a second, and now I'm gonna get started with the concept of constraint equations. Here is an example that tells what are the constraints and what they affecting the system. This is what we discussed last week as well. And what I have here is this crankshaft system. Now if I take a hold of the piston body of the crankshaft, and I'm going to move on the piston body to left hand side, other bodies will follow the certain way. The certain way is defined by constraints. So basically what the constraints are doing for us, it is limiting the motion possibilities of bodies. Remember that this body initially have these 3 generalized coordinates, but these generalized coordinates cannot change as they want and as they please. They can only change their numbers in a certain way, which are defined by constraints, these joints. And that's the case in reality as well, because connection rod, which is obviously this body here, cannot just leave the engine and go to cafeteria and come back. That's not possible because it is connected to piston and crankshaft. And that's it. And its lives is just, its role is to be between these two bodies, and that's it. Here too, we have to do it a similar way. And now I see that I got no more answers to my Socrative, so I will go and show the solution to you. So here it is. Okay, success rate, my guess today is that it's going to be 75%. Oh, look at that. So 82 is good. It's really, really good. Let's take this off and let's give a right answer here. Obviously this is a right answer because this is what we just discussed. So the variables are the ones associated to this guy and the one associated to this guy. Vector u bar is constant, so it's not variable, so it's not generalized coordinates. Back here. Now, constraints are the ones that are limiting the motion possibilities. And mathematically means that if I have this vector of generalized coordinates, number of components in this coordinate, this vector, depends on the number of bodies, of course. Then I have a certain number of constraint equations, so mathematical constraint equations that are saying that you can do this and only this, and you have to obey this rule. I have a certain number of these constraint equations. Here I have a total of NC number of constraint equations. Now relation of number of generalized coordinates, which is n, and the number of constraint equations, it's going to give you something extremely important, which is called number of degrees of freedom. Number of degrees of freedom tells you what are the different ways that your system can move. We'll get back to that in a second. But let's look an example about the constraint equation. Again, take your other stuff away, put your, browser off. If you're surfing in the internet, then follow me because you need to understand this. This is critical. So what I have here body A and body B. They're both potato-shaped bodies. But what I want to do here is that I want to introduce a revolute joint between these two bodies. So what that means? Revolute joint means that once I attach the bodies together by a revolute joint, then that particular point have to be common regardless what. So it means that the system can, there's two bodies, they can translate together like this, they can rotate together like this, and they can rotate like this, but this particular point have to be common no matter what. Okay, so if this point have to be common with respect to body A and with respect to body B, how is that we can describe that mathematically? Well, actually we do have tools to make it happen, because remember, we have the description of a particle. And the description of particle is this equation that first describes where is a translation of where the body reference coordinate system is located at. And then we can account the orientation of the body reference coordinate system. And then with help of vector u bar, we can go whatever place we want within the boundaries of and outside of the boundaries of the body. Okay, so that's when I'm following this equation, it takes me first here, then accounts the rotation and takes me here. So this is a point where I'm at when I'm using this part of the equation. Make sense? Okay. Then there's a right hand side of the equation. Right hand side of the equation is associated to body B. Now I'm able to describe the same point by using the same concept, but this time I'm going to use a body B, so I'm going to go with the body reference coordinate system B here, and I'm going to take orientation of body B into account, and then with help of vector u bar, I'm able to go to this very same location. Now if I'm going to put this definition equal than the definition with respect to A, that's going to be my constraint equation. I can see that there is some comments here. Okay, so nothing important. Okay, that's my constraint equation. So what I need to do the math. So here's my components of Rx associated to body A, rotation matrix of body A, vector u bar, same for the body B. And what I simply need to do is that I need to take everything and put it in the left hand side of the equation. So I'm multiplying this matrix by this vector. It's going to give me these two components. Then I'm going to take this guy to the left hand side of the equation. I change the sign here, multiplying this by this, changing the sign, and setting this to be equal to 0, meaning that this location will be common no matter what. And then I just need to check that that this appears to be well. Yeah, it's okay. Then the second row is similar thing. So y component here, this one multiplied by this one here. And then here I'm going to take everything to the left hand side of the equation. And once I do that, it's going to give me two constraint equations. Two constraint equations. Very, very mechanical. That, by the way, is a theory of multi-body dynamics. So here, everything we do is mechanical. So we're repeating the procedures over and over and over again. So one thing that is not allowed here is don't do heavy thinking, because heavy thinking will take you away from these procedures. So just follow the procedures, no thinking. That's what is needed here. Okay. Then we're going to practice this constraint equation many times, so no worries if you had a little bit of hard time to understand this explanation. But number of generalized coordinates, number of constraint equations, as mentioned earlier, they are very important for us, because those are the ones that can tell us what is a number or degrees of freedom. Meaning that what is the different ways that the mechanism can move. I will show you a few examples of, but basically the equations and ingredients you need to be able to express the number of degrees of freedom is the number of generalized coordinates, which only depends on the number of bodies, and the number of constraint equations. That's it. Now I know that it's getting late, it's almost 6 o'clock, and I've been saying already, I don't know, several times that you need to pay a full attention to me. One more time, please pay a full attention to me, because final thing that is extremely important to understand is what are the different scenarios related to number of degrees of freedom. And I'm going to explain that to you by using this crankshaft mechanism that is again shown here. You know, crankshaft mechanism, if you look at the number of bodies I have here, 1, 2, 3 moving bodies. So I have a total of 9 generalized coordinates. Then you know that the revolute joint requires 2 constraint equations. I have here 3 revolute joints. So it's 2 multiplied by 3. That's going to give me 6. And then translational joint that you don't know, but I'm going to tell you that that too needs 2 constraint equations. So I'm going to have a total of 8 constraint equations. So the number of degrees of freedom in crankshaft mechanism is 1. Okay? Now, if we're going to activate the crankshaft mechanism by a force, this 1 degrees of freedom is activated by a force, which could be a moment that is applied here, or it could be force applying here. Then this system, which have the 1 degrees of freedom, is dynamically driven system, because it's driven by a forces. That's the concept that is extremely important to understand. What I could do as an alternative is that I can introduce one more constraint. Remember, I have here originally 1 degrees of freedom. And I can take these 1 degrees of freedom away by introducing pre-described motion. Pre-described motion is constrained similar way that it is a revolute joint. And the pre-described motion could be related to, say, this body here. And I'm saying that this body have to follow this angular velocity no matter what. So that will introduce one more constraint equation. And it means that the number of degrees of freedom is 0. This system is kinematically driven. And you don't need to get an equation of motion to resolve the response of this system, because you can solve it kinematic, using kinematic analysis only. Then the final option is that there is too many constraints that the system cannot move. That's over-constrained system. Here it is. Over-constrained, so I have one more revolute joint, where the connection rod is connected to ground. Not going to work, so this system cannot move. So it's over constrained, no motion, because we're dealing with the rigid bodies. Or I have 0 degrees of freedom. I have kinematically driven system. Equation of motions are not needed. I can solve the responses by using just kinematics. Or dynamically driven system, where I do need to get the solve the system by using equation of motion. My final in-class quiz is this: number of degrees of freedom in kinematically driven system, which you can solve by using kinematic analysis, is, and then I have here choices: less than 0, equal than the 0, more than a 0, more than 100. Okay, here. So let's take a look, and with that let me see if I have many more slides for you today. Yeah, I think I'm gonna stop here, because the next one is kind of related to like how many constraints you needed in different cases, and then we're gonna practice a little bit how to compute the number of degrees of freedom. But here, so what's the number of degrees of freedom in kinematically driven system? Kinematically driven. This is a very, very important to know, because kinematical analysis can be carried out only for systems that are kinematically driven. And I get the answers. Kind of my headset is not too comfortable. It's kind of like feel a little bit not so nice. Okay. If I remember correctly, last time we got 76 answers, so I think that this is it. I think we are not going to get more than this, but I'm going to wait another 10 seconds or something. Okay, it's 77 now. Okay, so guys in the chat, so what is that you're saying? What is going to be the success rate? And the prediction there. If you guess this correctly, I'm gonna give you, I don't know, an extra point, extra in-class quiz point. Oh, I like you very much. So 100%, that's can-do attitude, definitely. But is it in reality? We'll see. Yeah, there's a history here. So if some of you are guessing this correctly, extra points. Okay, so here it goes. Record so far. This is a record so far, 90%. 90%. So it's good, really, really good, but not 100%. But 90% is good, but would be awesome to get 100%. Okay, what's the deal with this? Kinematic driven system, the number of degrees of freedom is 0, because all the degrees of freedom are eliminated by constraints one way or another. So that's how it goes. Now I see that Ansi was guessing this correctly. I'm not sure. And there is another one that guessed that correctly. So I'm going to count that when I'm putting together in-class quizzes. So, and now it's exactly 6 o'clock. So I'm going to close this streaming. And again, I need to apologize. This is still kind of learning to me. I mean, that I've been streaming the lectures before, but this full online is a little bit new to me, and for some reason my OBS is a little bit unwilling to cooperate, so that's why the streaming is more difficult than usually. Anyways, so with that, let's move on to Teams, and if any comments, any questions, any improvement proposals, let me hear that from the Teams meeting. Okay, thank you guys, and see you on Monday, of course.